All right, here we are again. So what we're going to do right now is we're going to finish this sample midterm, which we didn't quite finish, and because of that, the actual midterm won't need to be handed in until next Wednesday instead of this Wednesday because we weren't done. It's just that simple. Okay. So anyway, now one thing I do want to point out here is that there was an error last week, and I will show it to you right now. In question 30, I went back later on and I double checked and I discovered that, yes, there is a sign error in question number 30, right down here towards the end of all these many calculations. There was a sign error, which spoils the whole thing. So this is the actual answer right here. This was supposed to be a negative, and therefore, instead of plus 224i, this should have been minus 208i. So that's the only one that I could find. I would say the others are all fine. This one, though, I noticed it because I was double checking it, and sadly enough, I did make a sign mistake. And this is, again, a reason why you should always show your work. Good morning. Because this way, if I was grading myself, I could say, well, 98% of it is done correctly. So therefore, whoever did this only loses 1 or 2 points instead of the whole whatever it was, because all of the work is right there. So this should be a cautionary tale for you when you're writing out your own your own final exams. If you just write an answer with no work and it's wrong, well, that makes it very hard for me to give you partial credits. But this way, with all the steps, I can see what you've done. And if I realize that you've made a trivial mistake down here somewhere, I can still give you just about all the points because I can see what happened. So this is why. And also, it's easier to go back and make sure you haven't made a mistake. Realistically, especially with a test like this, you should be double checking all your results. And if you didn't write any of them down, it's going to be very hard for you to go back and say, did I do this correctly or not? And especially since you're taking it home and doing it, you'll have plenty of time to do this. This is not like a regular in-class exam. You do have plenty of time to double check everything. You really should take advantage of it, especially with such a complex topic like this one. Now, I'm not saying you have to, but I'm saying it's a good idea, that's all. All right. So especially something this involved, look at all those steps. There's so much going on here that this is really the only way to keep track of everything and to hopefully make sure that a mistake isn't made. And if it is, it'll be due to something that I can spot, and then I can help you out by giving you just about all the points. Other than that, we're ready to roll here for number 34. So hold on one second. Now, the one thing that's really annoying with Word is that the handwriting here is great. It's very convenient, but it does suck up a lot of memory. And so it's been my experience with Word that if I try to put too much handwriting on the same document, eventually it will refuse to save itself. And so I think I may have reached that point here. So what I'm going to do is just put the last few questions on a separate document. I'll call it part 2 or something along those lines. So I'm going to put this one away, and we're going to start from scratch with a brand new copy to avoid that little problem. So let me save this. Okay. And then I'm going to open up a fresh copy of this exam. And then we can get back to it. There we go. Oh, wrong one. Sorry, I'm in the wrong category. One second. All right, so we're just about ready to do number 33. That's right. All right, and by the way, when we're done with this, then we're just going to go on to chapter 4 because that's the next chapter. And so chapter 4 isn't quite as long. And actually, for that matter, neither is chapter 5. 3 and 2 were actually quite long. The coming chapters, 4 and 5, are not quite as long as the others, so they won't take as much time. And then whatever comes next. Oh, by the way, you know what that reminds me? One more thing we better talk about before I completely forget about it. We actually have a day off coming up. Somewhere along the way. What week? Oh, here it is, the 14th. That would be 2 weeks from today. Okay, so just make a note of it somewhere if you haven't already. 2 weeks from today, we do not have class. The school has decided apparently that will take the place of a spring break. They gave us 3 individual days off. And so for us, that will take place 2 weeks from today. So we'll have a regular class next week on April the 7th, but then the week after that, we will be off. So I'll remind you next week as well, but we are going to miss a week. So just, hopefully if you haven't written that down in your calendar somewhere, you should do that right now. So that will affect the, what topics we cover, but just be aware that there is a holiday in 2 weeks. Not really a holiday, it's just a day off. They randomly pick 3 days to give us off, and that happens to be one of them. All right, I think that's all that I also wanted to say. All right, let's get back to it then. So we're going to start with number 33, and let me save this real fast. Today's the 31st. All right, so here we go. So we're doing the same thing basically in this section. We're basically relying on our knowledge of I and the powers of I, which we may as well review that right now. Let me go back to the notes and remind you how that works. Hold on one second. This is chapter 3. So in the notes, we build up a little chart somewhere. Let me go find it. I think we did. Maybe not. All right. Well, the logic here is this. All right. Well, we can do this from scratch. It doesn't really matter. The idea here is that if you recall, I is the square root of -1. Yeah, let's switch that to black. I is square root of -1, of course. I squared is therefore -1. I cubed would therefore be -I. I to the 4th would be -I times I, which is -I squared, which is +1. Then the cycle starts all over again. I to the 5th is the same as I to the 1st, which is just I. I to the 6th is -1. I to the 7th is -I. And then I to the 8th is +1. Okay, so the cycle just keeps repeating itself. If we needed to know, for example, I to the 9th, it would just be I, and then I to the 10th, I to the 11th, and I to the 12th. So this is extremely important. So it will help us simplify these results. If we don't simplify them, they'll really be very, very complicated. But because of these properties, we may as well take advantage of them. All right, now let's take a look at this one. Now we're going to apply FOIL here, or we could apply FOIL here. It's not mandatory, but we certainly want to take advantage of this. So of course, F would be here. O, 8I cubed. Inner, or I, would be minus 8I to the 4th. And then finally, last would be minus 4I to the 7th. Okay, so remember, I to the 4th times I to the 3rd equals I to the 4 plus 3, or I to the 7th. Okay, so now we consolidate these, and you can see none of these can be combined with each other, but we do have a lot of substitutions available to us. So let's take a look at them. So I cubed is negative I to the 4th is 1, and I to the 7th is negative I. Okay, now equals 16 minus 8I minus 8 plus 4I. So we consolidate the two constants and the two i's. And in spite of its messy appearance, we end up with something that's quite simple. Okay, quite simple indeed. And that would be our final result. Okay, very good. All right, now how about this next one? All right, let me leave it there for a minute so you can catch up. So you can use FOIL to multiply those out. And then, of course, having this list in front of you. Now, if you don't, you can make up your own list if you want to for reference. But basically, it's just based on the logic that I squared is negative 1, and the rest of them just fall right into place from there. Okay, now, what about 34? Now, these are ratios. With ratios, what may happen, not always, is that we can take advantage of the complex conjugate. In other words, here's what we can do. So we just remind ourselves that 2 plus 4i is the complex conjugate of the denominator, which is 2 minus 4i. So what we will do is multiply the numerator and the denominator by this complex conjugate. And the only purpose for doing this is to simplify it. All right. It's not going to change anything, of course. It's just going to be simpler. So in the numerator, we can apply FOIL. Let's do that right now. F is 6, O is 12i, I is 10i, and then last is 20i squared. Now here you notice there's one substitution we can make. I squared is negative 1 from our chart. Okay, so therefore, we can replace this with negative 1. And so our numerator is now negative 14 plus 22i. Now for the denominator. Now the denominator is 2 minus 4i times 2 plus 4i. Okay, so first is 4, outer is 8i, inner is negative 8i. And then last is negative 16i squared. Okay, so we consolidate. Now these two, of course, drop out. So we'll have 4 minus 16i squared. 4 minus 16 times negative 1. 4 plus 16 equals 20. Okay, well, that worked out pretty well because you've now got the ratio of negative 14 plus 22i over 20. And because they're all even numbers, you can actually simplify this a little further to negative 7 plus 11i over 10. Now, that's not absolutely necessary, but it might be a good idea because remember, our goal is to make this as simple as possible. And also, whenever possible, we want to eliminate any imaginary numbers that find themselves in our denominator. Okay, so we always prefer to have real numbers in the denominator of any expression. It's mathematicians prefer things done a certain way, and this is one of those cases. It's like with radicals. Have you ever noticed mathematicians like to get rid of radicals in the denominator whenever possible? It's the same idea. Is it necessary? No, but that's how it's supposed to be done. All right, well, let's try these two. Now here, we don't really have a complex conjugate to choose from here. This will be a little bit trickier to simplify. Well, actually, yeah, because remember, a complex conjugate only involves if you have a plus bi, a minus bi. They have to be in this form to be considered complex conjugates. We don't have that here. So here's what we'll do. We'll multiply out the numerator and see what happens. Now, by the way, just because there's a ratio here, it doesn't guarantee that there's any simplifications available. It may just be that we have to leave it the way it is. Okay, so it's not always possible to simplify one of these expressions. But we try, we do our best, okay? So once again, we'll apply FOIL here. So here's F, here's O, here's I, and here's last, minus 2i cubed. Okay, so none of these can be consolidated. And now remember, I squared is negative 1. I cubed, if you go back to our chart, is negative I. Okay, so we're going to have 15 plus 10. This is our numerator, by the way, plus 3i plus 2i. So we'll have 25. Now the denominator, if you recall, is 1 plus I cubed. But once again, I cubed is negative I. So we can write that as 1 minus I. So when we're done, the entire ratio, the final result will be 25 plus 5i over 1 minus I. And that's it. We can't really make it any simpler than it already is. Although I suppose, now that I think about it, let's try this just in case. Now that it's written this way, though, we actually do have a complex conjugate. Why don't we give that a shot just to see if it helps? It may not. There's no guarantee. So let's try this. So the complex conjugate of 1 minus I would be simply 1 plus I, because all you're doing is changing the sign of this I. All right, well, let's see what we end up with here. Hopefully it's worth our extra trouble here to do this. So let's move this down here. 25 plus 5i. All right, here we go. 25 plus 5i times 1 plus I. Let's apply FOIL to that. 25 for F. O is 25i. I is 5i squared. And last is, sorry, no, it isn't. That one is 5i, my fault. And then the last one, though, is 5i squared. All right, so let's try that again. F is 25, O is 25i, I is 5i, yes, and last is 5i squared. So we have 25 plus 30i plus 5i squared. And of course, once again, I squared is -1. And then we finally end up with 20 plus 30i. That's our new numerator. Now, our denominator, I 1 plus and 1 minus I. So now in the denominator, we have 1 minus I and 1 plus I. So once again, we'll use FOIL. O is I. Inner is -I. And last is -I squared. 1 plus I minus I minus I squared. Okay, so these two clearly cancel out. 1 minus I squared. What do you know? So the denominator is 2. So it looks like we're getting somewhere here. So now the final result will be 20 plus 30i over 2, which very clearly is just 10 plus 15i. So yeah, that reduced very well, because remember the original expression was this catastrophe all of this time ago, and now we've reduced it to this. So I think you'll agree we've seriously simplified it to something much more manageable. All right, I'll give you a minute to catch up. All right, so now this is, wow, look at this one. All right, well, all we can do, we'll just have two foils. Let's try the first one. All right, here's first, outer, inner, last. Okay. Two minus 4i plus 6i. So these two consolidate to 2i. And of course here, I squared is just -1. That's our numerator. And then in our denominator, we have 1 plus 2i, 1 minus 3i. All right, 1 plus 2i is multiplied by 1 minus 3i. So let's apply FOIL to that. F is 1. O is minus 3i. I is 2i. Last is minus 6i squared. So here these two consolidate to form minus I. And I squared, of course, is -1. And then, of course, that ends up with 7 minus I. And so finally, our final result is the ratio of those two. So we'll have 14 plus 2i all divided by 7 minus I. And that's it. You can't get it much simpler than that. Okay, now the vertex form, yes. So let's go back to the notes for a second and quickly double check or review for a second how this works. Just as a quick reminder, we have a multiple step procedure. I don't remember exactly where we found this. Actually, I think this was chapter 2, wasn't it? Yeah. Let's check that out. Just a quick reminder how this works. Oh, maybe it was chapter 3. How about 3a? There we go. So the key characteristics of a parabola, of course, are the vertex, the axis of symmetry, the zeros are solutions, and the intercept. Right now, we're just interested in the vertex. So remember, the vertex, first of all, is the point where the parabola either reaches its maximum or its minimum point. Okay, so just a quick reminder. For each one of these, if A is positive, this would be your vertex is the minimum value of the function. When a is negative, you have something like this. It's the maximum value. That point is what we're looking for. This is the vertex. Now, we had formulas to help us with this. Oh, let's close this. Now, how does this work? So we wrote the point. Actually, the way we write this form is in a very specific way. Okay, so that's how we write it. The vertex itself is the point. Nope, not that one. It's the point h comma k. So in other words, when we find the vertex, we're replacing the x coordinate. The x coordinate is the h. The y coordinate is the k. We simply plug these into this formula. The a, remember, is taken from the original quadratic formula. Remember, f of x always equals ax squared plus bx plus c. So that a just simply refers to the coefficient of x squared, which again is what determines, the sign of it at least, determines whether this vertex is the maximum or minimum value of that expression. But even then, we need to know the formulas. Okay, there's a formula, if you recall. It's right here. H equals negative b over 2a. And k is f of h. Okay, so in other words, once you plugged in these numbers, these letters, and solve for h, then you plug h into the original function and solve for k. Once you have that, you've got your vertex, which you can then use to write out your expression, or your, in this case, your quadratic equation, in the form of the vertex form. All right, so let's do this first one. So the first thing you do is identify a is 2, b is negative 14, c is 8. And then you can solve for h very easily. H is simply equal to, in this case, minus a minus 14 over 2 times 2, 14 fourths, or 7 halves. Now the k is f of h, which is f of 7 halves. So you go back to the original equation and substitute for every x 7 halves. All right, so let's do it. Now, of course, you're going to wind up with a very messy expression because of all the fractions. 7 halves squared is 49 fourths. Don't forget to square both the numerator and the denominator, by the way. Here, though, when you multiply 14 by 7 halves, you're only multiplying the 14 by the numerator. So you've got 98 halves. And then you have plus 8. Now, let's just take this one step further. You've got 98 fourths minus 98 halves plus 8. Now, in order to consolidate these into a single term, we need to have or find a common denominator. Let's try 4. And so in order to get them all into that form, I'm going to multiply this one by 2 halves and this one by 4 over 4. Okay. So then we have 196 over 4. All right, and so when you add up these numbers, 98 minus 196 plus 32, you have minus 66 over 4. And then you can actually reduce that a little further to minus, let's see, 33 halves. That's as simple as it's going to get. So what that means then is that the H is 7 halves and K is minus 33 halves. So that the vertex is the point 7 halves, comma, minus 33 halves. So if you had a plot of this function, in fact, you know what? We've got time. Let's go grab Symbolab and look at this thing. In fact, while you're at home doing this test, you can feel free to check out Symbolab and just graph these functions if it helps you. You wouldn't be able to do that in the classroom, but here we might as well take advantage of this. 2x squared. It's really just a tool for helping you visualize what you're doing. 2x squared minus 14x plus 8. Let's see what it looks like. And right there, as we suspected, 7 halves, comma, negative 33 halves is our vertex, meaning our minimum point, because this one faces up. Now, the last step is to write this in that special form right here. So in other words, we're taking the original equation and rewriting it in a slightly different form. So that means in this case, we could write f of x in the following way. F of x equals now remember, a in this case was 2. A is 2. And in the expression, in the parentheses, we'll put x minus 7 halves squared. And then k is, we'll add, or basically we're adding negative 33 seconds, so we're subtracting it. That's the final result. After all that work, this is what we're aiming for. All right. So they're all the same. All right. All these problems are exactly the same. All right. So let's skip ahead to the next one. All right. So here we have A is 3, B is 5, C is negative 9. All right. Now, remember what we're trying to do here. We're solving for H. H equals minus B over 2A, which is minus 5 over 2 times 3. Great. Now, K is f of H, or f of negative 5/6. So we've got 3 times minus 5/6 squared plus 5 times minus 5 over 6 minus 9. So we'll have the same problems here. Because it's a fraction, we'll end up needing a common denominator to bring them all together into one term. Okay. So actually, I'll tell it. Let me draw out all the steps here. I'm multiplying the minus 25 over 6 by 6 over 6. to make sure that they all have the same denominator. What I really need is 36 over, I want them all to be in terms of 36. Okay. So this one will be 150 over 36. And over here, 324 over 36. All right, so when you combine those, 75 minus 150 minus 324, we have minus 399 or 36. Now, you know, this one can be reduced. Why don't we divide the numerator and the denominator by 3 first? This is negative 133. And I think that's it. I don't think this can be reduced any further. All right, 133 over 12. So finally, when all the dust settles, you have H equals negative 5/6. K is negative 133 over 12. So HK, the vertex, okay. And so now it's time to rewrite this function in the form, vertex form. So what do we have? So from way back in the beginning, remember A was 3. Now here we're subtracting a negative number. So this is actually plus 5/6 squared. And then we're adding a negative number here. So this is the form that we need to write this in vertex form. All right. All right, well, that one's done. All right, so now for this one, A is 1, B is negative 1, C is 5. So therefore, H equals minus B over 2A minus 1 over 2 times 1 is a half. All right, and remember that K is f of H, which means we have, here's the function, we have 1/2 squared minus a half plus 5. And this gives us 1/4 minus a half plus 5. So the common denominator we can use here is 4. All right, so we've got 1/4 minus 2/4 plus 20/4 equals 19/4. So the vertex is therefore 1/2, comma, 19/4. And then the equation becomes plug in the numbers. In this case, remember, a was 1, so this is especially simple. X minus 1/2 squared plus 19/4. All right, I think there's only one more of these. By now, we're getting pretty good at it, I think. Yeah, there's one more. All right, so let's do this one. So we note right off the bat, A is -1, B is -8, C is 10. So therefore, H equals minus B over 2A minus 8 over 2 times -1. That's positive 8 over -2. Actually, let me add that in here. Okay. And then what about K? So I have -4 squared minus 8, -4 plus 10 minus 16 plus 32 plus 10 equals 16. Is that right? Nope, sorry, 26. Okay, that's better. All right, so the vertex and by the way, since this one has a -a, that means that whatever this thing looks like, let's see, what does that look like? It'll be up here somewhere. In other words, this is the maximum because the A is negative. It's facing down. All right, now as far as the equation goes, okay. So we plug in the numbers. A again was -1. Now H is -4, so -4 is +4. And then we have 26. And that's it. All right. Well, now we get to do some division. Woohoo, some division, yes. What could be more fun than that? I don't know. So, all right, now we're going to look for the quotient and the remainder. So remember, this is the procedure where you take the denominator, and you write it in such a way that it's basically just long division. And in the numerator, let's see, inside here we have x squared plus 6x minus 5. So remember, what are we trying to do? We're trying to eliminate as many of these terms as possible, 2 at a time. So if I multiply this expression by x, I get x squared plus x. Now I'm subtracting, but here we have to be extra careful because I have to change both of these signs. This is now negative. And the point is to get rid of this one no matter what. And whatever's left, I bring this term down to try again. So here I'll try 5. And when I multiply this expression over here by 5, I get 5x plus 5. Subtracting this entire expression, this becomes negative, this becomes negative, these drop out, and I'm left with negative 10. So what this means then is that the remainder, sorry, the quotient is what I wanted to say. The quotient is first. The quotient is up here. The remainder is right here. Okay. So therefore, we can just say that the quotient is x plus 5, and the remainder is at negative 10. All right. Now, most of these will not work out nicely. I mean, you'd like to think that once in a while we'd get an even result with no remainder, but sometimes it happens and sometimes it doesn't. So like this next one is looking especially unpleasant. You'll see what I mean when we finish it. All right, let's try this one. So we start out, we'll try 2x. That gives me 6x squared plus 20x. When I subtract, this becomes negative, this is negative. I've got minus 28x, bring down the 12. Yeah, you see the problem. In order to get a 28 here, I'm going to have to subtract, if you can believe it, 28 thirds. Because if you multiply negative 28 thirds times 3x plus 10, you'll get minus 28x minus 280 thirds. I believe 280 does divide evenly by 3. Let's see what that is. Wait, maybe not. Oh, no, it doesn't. Ooh. All right, that's pretty rough. Okay, so we're going to have minus 28x minus 280 thirds. This becomes a positive. This becomes a positive. Oh, look at this sum. So here I have to consolidate for my constant. This is my remainder, 12 plus 280 thirds, which can be rewritten as just to get a common denominator. 36 thirds plus 280 thirds is 316 over 3. And wow, I think that's it. It can't get any simpler. So therefore, the quotient is 2x minus 28 thirds. And the remainder is this term 316 over 3. Wow, that was a mess. All right, so let's see what's next. Okay, let's see. We've got x plus 8 is divided into 12x squared minus 3x minus 6. Okay, so this one may not be quite as messy. So here in the top, we start with, let's try 12x. So 12x squared plus 96x. Ooh. So you have minus 99x, bring down the 6, the negative 6. So then here we can try 99. Actually, we need negative 99. And 99 times 8 is 792. So we subtract. These both become positives. So this one is now negative 780. Oh, sorry, positive 786. All right, so, well, that one wasn't quite as painful. So therefore, the quotient in this case is the 12x minus 99, and the remainder is 786. Well, it could have been a lot worse. All right, but that's the final result. All right, one more. X plus 3 is divided into 6x squared plus 12x plus 18. So then we'll try 6x. All right, so we subtract. This becomes negative. This is negative. These drop out. Here I've got negative 6x plus 18. And then for this part, we'll put negative 6. This becomes a positive. This becomes a positive. These drop out, and we have 36. Okay, so for this one, this is a pretty straightforward one. Quotient is 6x minus 6. Remainder is 36. All right. Now, these last few are pretty straightforward. All we have to do is find the slope of a line. I like that. All right, so we've got 2 points. Now remember, the equation of a straight line is simply equal to y equals mx plus b. And m is delta y over delta x, which is y2 minus y1 over x2 minus x1. So you can think of this as x1, y1, x2, y2. So we start by solving for the slope. 8 minus 5. Remember, that's y2 and y1. Then for the denominator with minus 2 minus 3. Okay, so the slope is negative 3/5. Now the intercept can be found by doing the following. We rewrite this equation as minus 3/5 x plus b, because we know the slope is negative 3/5. And we can pick either one of these points to plug into this formula, and we'll end up with b. So we substitute either point into this expression or this equation to find b. All right, let's just pick the 3 and 5. How about that? So that means y is 5, x is 3, and so therefore 5 is negative 9/5 plus b. I'll add the 9/5 to both sides. Now I need a common denominator. Let that be 25. 5 rather, sorry, 5. That's it. 34/5 is your b. So the final result is that the equation is y equals minus 3/5 x plus 34 over 5. That's your equation. Okay. Okay, so the same thing is happening here. M equals, so this is x1, y1 is 2, y2. And so M equals y2 minus y1 over x2 minus x1. So we have 13 minus 5 over 3 minus 0, 8/3. So we have 8/3 x plus b. So now we replace, let's try 0, 5. To find b. All right, so y equals 8/3 x plus b. And since the point we chose is 0, 5, we have 5 equals 8/3 times 0 plus b. Well, that worked out rather well. 5 equals b. So the final result is that y equals, for God's sake, y equals 8/3 plus b, 8/3 x plus b. Nice. Now, these next two are a little bit different. I mean, they're really the same thing, only they've been written up a little differently. That's the only thing. It's like, for example, here, this is equivalent to saying that when x is 2, y equals 12. Okay, so you have the first point, negative 212. And here, this is the equivalent of saying that when x is 5, y is 8. So therefore, you have the point 5, 8. And now the rest is exactly the same, all right? In other words, you're going to set up the slope as, let's say this is 1. This is y1. This is x2. This is y2. So this ratio would therefore be 8 minus 12 over 5 minus 2, which is minus 4 over 6, 7 rather. And that's it. We can't simplify it any further. All right, so the slope is 4/7, negative 4/7. And we'll pick one of the points at random. Let's try 5, 8. Okay, so let's plug in those numbers. 8 equals minus 4/7 times 5 plus b. All right, so I'll add the 27ths to both sides. And now I need a common denominator. Let's use 7. Equals b. And so we'll have 56/7 plus 27 equals b. And so when we're done, 76/7 is the intercept. And so finally, the equation of this line will be, all right, remember the slope was negative 4/7 plus 76/7. Okay. Now for this next one, we have the same setup. It's just a similar way of getting at the same results. We're told here that when x equals 0, y equals 4, and when over here we're told that when x equals 10, y is 20. So you have 2 points, 0, 4, 10, 20. All right, so the slope, and again, think of this as x1, y1, x2, y2. The slope equals 20 minus 4 over 10 minus 0, which equals 16/10, or we could think of that as 8/5. Okay, so we now know that y equals 8/5 x plus b. And let's try the point 0, 4. to find the intercept. All right, and that makes things a lot easier because that means 4 equals 8/5 times 0 plus b. 4 equals b. So that means the final result, the slope was 8/5 x plus 4. And that's that. All right. Well, you know what? It's hard to imagine. Finally, at long last, this whole ordeal is over. We're done with the reviewing. If you, this should be the perfect crystal ball for your actual midterm. So if you can do what we did here, you're aces. Okay, you'll have no trouble whatsoever with the actual midterm. None. You just have to be careful. That's really always the bottom line. Be careful and write out all the steps whenever possible, so that I can give you partial credit if something does go wrong, which it can very easily. All right. So now we can finally, after all this time, we can start to take a peek at chapter 4, which I think I mentioned this once before. Turns out to be one of the more important applied areas of this course. We see these results regularly in other disciplines. Obviously some of these concepts are not going to show up as often as others, but what we're about to do is extremely important in the real world. And in fact, there's quite a few real world examples in chapter 4. And there's a reason for that, because this type of material lends itself very nicely to real world applications. So let's take a quick peek at this. And what we're introducing here is what we will call exponential and logarithmic functions. Now, they look scary at first, but they turn out to be fairly straightforward. And a lot of this can be done with your calculators as well. They do have this capability. Even if you're using the iPhone for your calculator, it should have a lot of what we need on it. Yeah, that's it. Everything else that we're seeing from this point on is not on the midterm. This is new material. What we're seeing here is going to be on the second midterm, but not the first one that's due next week. Okay, so the first 3 chapters are completely done. We did all the problem sets. We did the midterm, sample midterm. We practiced and we went over the actual notes. And so we're ready. We're as ready as we're going to get for the first midterm. This now is completely new and it is not on the first midterm. Okay, so you can breathe a sigh of relief, but it will be on the second midterm when that eventually rolls around. Okay, the second midterm will actually be shorter than the first one, if I remember correctly. But usually the first midterm is the hardest of the entire semester. It's been my experience, because you're still getting used to the content, and it often ends up being the longest of the 3. So if you do well in the first midterm, you should be fine for the second midterm and the final. Especially because the later material that we'll be wrapping up with at the end of the semester is really more applied than what we're seeing here, which is a little bit more abstract. So all right, well, we'll just keep going and we'll see how it goes. But anyway, this is the formal definition of an exponential function. Now, you can see what makes this so unusual is that x itself is now suddenly an exponent, which we haven't seen before. If you notice, if you look at all the equations that we've done before, we might have x to any given power, but this is the first time x itself was an exponent. Oh, yeah, just take a picture of it and email it back to me. That'll do just fine, unless you have a scanner. Also, oh, you know what that reminds me? Maybe it was this class. Somebody told me about this app that's available for the iPhone. It's called, let me write this into the chat room here. Now, I don't know anything about this. Remember, I'm not a tech guy. But I was told that this app that's available for your iPhone called Genius Scan acts like a little tiny scanner, And I've been told that it does very good quality work. I don't know if that's true or not. All I'm telling you is what I was told. If you don't want to bother with that, just take the pictures, but just make sure that they're legible. Okay. It's easy with documents to take bad pictures because first of all, there can be glare on the page, especially when you're writing with pencil. It can be very hard to read it. And if it's too small or if there's something else going on, before you send it to me, just look at it yourself and make sure you can read it. Because if you can't read it, I can't read it. All right. So, in other words, take care to make sure that what you are sending me is legible. Also, to the extent that's possible, not that it really matters, but for this one, it would be easier for me if you send it to my purchase account rather than my own account, just because this way everything will be together in one place. And, obviously, if your name is on the documents, that's helpful. Just anything to avoid any problems will be very much appreciated. All right. Now, I've also been told that this notes thing that comes with your phone automatically, supposedly, also has some scanning capability as well. And again, I'm in no position to tell you whether that's true or false. This is what I've been told. And another possibility here too is this. If you own a printer, you can use it to create what are called PDF files, and you can email those to me directly. So besides the camera phone, you have a few other options. I'll leave it up to you to decide which one you want to use. Whatever works for you. Again, all that matters to me is that I can read it. That's the only thing that I care about. Can I read it? All right, so just keep that in mind. By the way, is anyone here familiar with any of those products? No, okay. Well, that's all right. I mean, like I said, I'm not exactly Mr. High Tech here. So I have to rely on people to tell me about these things that are available. That's just the way it is. I think we've all gotten used to that idea that when it comes to technology, the younger you are, the more you probably know. That's just how it works these days. Okay. So I don't mind people, giving me information because I expect to be ignorant about these things. In fact, if you have any ideas, you can always feel free to tell me, like, hey, did you know about this product or that product that's available on the iPhone? I want to know about it because I'll never find it myself. All right. Well, anyway, let's get back to this. So, like I was saying, this is the first time we've ever seen x be the actual exponent. So that's how you know something different is going on here. And the properties of these functions are quite interesting. Now, here, a is meant to represent what we'll call the initial value, and b is called the base. So the only constraints we have are that a cannot be 0, because then you would just have 0, and then b cannot be 1, because otherwise you just have the constant a. 1 to the x power would just be 1, and you would just have a constant. So other than that, anything goes. Now, before we go any further, let me show you in Symbolab what a typical exponential function might look like. All right, let's go over there. I want you to see what this thing looks like. Let's say we have 3 times 2 to the x power. All right, so let's see how it reacts to that. Oh, no. Oh, wait, sorry, I didn't hit the go button. Ooh, now that's interesting. Now, if you notice that on the horizontal axis is an asymptote to this function. It will never quite reach the point where y equals 0. Okay, in other words, there's no value of x that can make y equal to 0. In addition to that, if you notice, the y is never going to be negative. The x covers the entire real number line, but y is bounded from 0 up. In other words, y must be a positive number. It cannot be 0. So somewhere up here, they have the domain and range listed. So for the domain, we have the entire interval negative infinity to infinity. But the range, if you notice, we have that round parenthesis, which means 0 is not included here. It's everything from 0 up to infinity, not including 0. Now, if this constant here, or as they said in the slides, the initial value is negative, or if this exponent is negative, then everything will change. Like what? Let's see what happens when this becomes negative. Okay, so now it's just the opposite. The range is all the negative numbers. The domain isn't changing. The range has got to be negative. There's no positive y's. And so if you look at up here, there it is. Everything from negative infinity up to 0, not quite including 0. Now let's see if we can change the exponent to negative x. I'm not sure. Let me see what I can do here. Let's see what that looks like. Oh, so it's the reverse of what we had before. It's in other words, from left to right. Remember before it came up like this? Now it's basically been flipped around from left to right. So the range and the domain are the same as when we had positive x in our exponent. How interesting. So the changing of the sign just reversed the direction in which the function is facing. And then if I now change this to -3, well, you can probably guess what's going to happen. That's right. Okay, so there you go. Now, let's go back to the original function. Now, you might ask yourself, when in the world would you ever run into something like this? I will take your mind back to biology class in high school. And you might recall, you may have even done experiments with this. This is how, although of course now with many real world examples, we're restricted to the first quadrant, meaning this area here. That would be the case if you're thinking about the growth of a colony of bacteria. You might recall from high school biology that bacteria grows very, very, very quickly. So if you started with this much bacteria, pretty soon you'd have this much. And yes, it grows really fast. But it can't be negative, so you would only be looking at the first quadrant. Now, later on, we'll see that if you're looking at investing money for long periods of time, it can behave in a very similar manner. Although typically what happens is it grows very slowly at first, and then it starts to really increase quickly. But there's many different applications for these types of functions, which is what makes them so popular. Wow. How cool is that? So, wow, it doesn't look like much, but that's a pretty fun little function. So just as we saw, as long as this a was, remember when it was positive, this is the case where a is positive. And this is what it looked like when a was negative. All right, well, I've run desperately short of space, but you get the idea. So just based on Symbolab, we could see that when a is positive, it looks like this. When a is negative, it looks like this. So that means the range is either everything from above 0 or below 0. The intercept, oh, here's an interesting point. I didn't point that out. This, of course, y equals 0. The horizontal axis is the asymptote in all cases. But in addition, and I neglected to mention this, the intercept is 0, comma a. So let's go back to Symbolab and confirm that. Let's go back to our original function, this one. And when we look at the graph, right there is 0, comma 3, the y-intercept, because a is 3 in this case, all right? This 3 is the a. So no matter what happens, that intercept is always 0, comma a, or 3 in this case. And you can see why, because at this point x is 0. If you plug in 0 here, this expression becomes 1. So therefore, when x is 0, the intercept, or the value of a, is just equal to this a here. All right, what else do we need to know about these functions? Oh, I did have it. So this is the Excel version. You can see that it actually turned out fairly well. Excel graphs are kind of a flip. You never know how they're going to turn out. But yes, this is exactly what we saw in Symbolab. And the intercept, yep, we proved that. Okay, so now we're going to consider the idea of exponential growth. Like I mentioned earlier with the bacteria are assumed to grow at an exponential rate because the colonies, they feed on each other and they just get bigger and bigger and bigger. So this is something that happens in the real world. But now I say by the old clock that it's time for our break. So when we get back, we'll consider our first example of exponential growth. All right. So let's do it. Let's have our break. And when we get back, we'll dive deeply into this exponential growth topic. All right. All right, let's get to it. So here we are, exponential growth. So this is our function again. And once again, A and B. A is the so-called initial value. B is the growth factor, which determines how quickly the function increases. All right, so remember before, with Symbolab, we have 3 times 2x. So therefore, 3 is defined as the initial value. And this B, this number 2 is the so-called growth factor. All right, now here's an example. Suppose that a painting A, is currently worth $100,000 and it grows in value at a rate of $2,000 per year. Painting B, on the other hand, is currently worth $100,000, but instead of growing $2,000 a year, it grows at 2% per year. So what we're going to do is define a function for each of these. So for A, this is a simple linear function. And T, by the way, here is time, where it takes the place of X, time here and time here. So we start out with 100,000 when T equals 0. Today is always assumed to be T equals 0. 1 then would represent 1 year in the future. 2 would be then 2 years in the future, et cetera, et cetera. So if I plug in any value of T, I'll end up with the value of the painting at that point in time. All right, where B though, yes, and again, T equals 0 means today. T equals 1 represents 1 year in the future. T equals 2 is 2 years in the future, et cetera, et cetera. Now, that's the function for A. It's a nice, simple linear function because the growth is constant. Every year, the painting gains $2,000 in value. On the other hand, B is different because the amount that it grows is different. The percentage is always the same, but the amount is going to be different every year. And that's the key to the whole thing. So it turns out that this is an exponential function. And if you look at it carefully, A is the initial value. This is A. And it starts out at 100,000. And then after that, the growth value is 1.02. What that means is that it increases by 2% per year. And T is the time that we're looking at. So if we plot these together, you'll see what's happening to the values of these paintings over the next 30 years. And you can see that it's very close in the beginning, but after a while, the painting that grows at 2% per year starts to grow very quickly in value, whereas the painting that gains $2,000 every single year, the growth rate is linear. In other words, it just keeps going up by 2,000 every year, no matter what. Whereas here, the increase is actually changing over time. It's increasing at an increasing rate because 2% is being continuously applied to a progressively larger number. So over time, painting B gains in value more than painting A. And so this is a simple example of the difference between linear functions and exponential functions. Now, what we can sometimes do with these cases is we can take information about an object or a value of something or other, and we can solve for the growth rate. Okay, so for example, here's a good example. This is a nature example. Suppose that in 2006, 80 deer were introduced into a wildlife refuge. By the year 2012, the deer population had reached 180, more than double. If the deer populations typically grow at an exponential rate, what must have been the growth rate in this case? So in other words, what we're solving for now is B. So we're going to call this N of T for number of deer at year time T. And now we have to be careful with time. We don't want to use 2006 and 12 as our time. What we'll do instead is we'll count year 2006 as year 0, the starting point, which means that 2012, because it's 6 years later, we'll call that T equals 6. All right, if we don't do it this way, we'll get the wrong numbers in our formula. All right, so Here's the exponential growth function. It starts out with its standard form, A, B, T, and we plug in there all the numbers that we have. For example, this tells me that in 6 years, the deer population is 180. Oh boy. I'm sure you're hearing all that racket. They've just chosen today to cut the grass where I live. And so it's going to be noisy for a couple of more minutes. Sorry about that. It's really obnoxiously loud too. I don't know how much it's coming through, but it's pretty bad. But anyway, so we started at 80 in 2006. 6 years later, the population is up to 180. So I'm going to now solve for B. And you'll see that 180 over 80 is equal to B to the 6th, or 2.25 equals B to the 6th. And so what we're going to have to do in order to solve for B is, very clever. We're going to raise both sides to the 1/6 power. Okay, that's what we're going to do. So in other words, by starting out with 2.25 equals B to the 6th, if I take 2.25 and raise it to the 1/6 power, and I do the same thing over here, what I have over here, now remember, when you have an expression like this, if you have, let's say, x raised to the a power times 1 over a, this equals x to the 1 power equals x. Okay, so in other words, the 1/6 was chosen to cancel out these two numbers. So we're left with b equals 2.25 raised to the 1/6 power, which is 1.1447. So this is the growth right here. The 1 represents the initial value. This is how quickly the population grows every year. And so 0.1447 is the same thing as 14.47%. And in this case, it happens to be per year. So that means the deer is growing at a rate of 14.47% per year. Now, this potentially could be very useful because you could take, let's say, a stock, and you could figure out how much you paid for it and how much you sold it for, and use that information to determine what kind of rate of return you earned during that time period. In fact, why don't I throw that example in here right now, because I like that example. Let's just say, for example, that suppose that an investor paid $100 for a share of stock in 2010. The investor was able to sell the stock in 2020 for $1,240. Now, you might say that that doesn't sound possible, but some companies like Apple and Amazon, their stock price definitely goes up at around the same pace. So what was the annual rate of return to this stock? Okay, so let's just define the function. I'll use the letter P to represent price at time t. Okay, so let's say that 2010 represents year 0. In 2020, we're looking at year 10. Okay, now A, the initial value is $100. B, the final value is 1,240. So if the original function looks like this, AB to the t power. All right, hold on. Boy. I'm going to turn this into a superscript. That's my function. Now I'm letting t represent time, of course. And So PT, I'll use that to represent the price at time t. Okay, so what we're trying to solve for, oh, wait a minute, I did something wrong, didn't I? Yeah, no, something's not right. I'm solving for B. What is going on here? No, oh, I know what the problem is. Okay, sorry, I know what I screwed up. It's not B that's 1240, it's P of 10. So A in our function is actually P of 0, which equals 100. All right, let me get this straightened out. That's better. And then B is P of 10. No, sorry. P of 10 is 1240. Okay, where P is price at time t, that's better. So this is the initial value of the function, but what we're actually seeing here, actually, let me move this on to the next slide. With this as our starting point, the A is actually equal to P of 0, which is 100. So, and P of t, P of 10, P of 10, as we've already seen, is 1240. So what that means is that when I make these substitutions, we have 1240 equals 100 times B raised to the 10th power. There we go. All right, hold on. I have to, making superscripts is a little bit awkward in PowerPoint. All right, so now this is where we want it to be. Okay, so what we want to know is what kind of rate of return do we get from owning this stock? Okay, so in other words, the form is saying that if you start out with 100 and you grow at rate B for 10 years, the painting will be worth $1,240. The stock will be worth $1,240. So how do we solve for that? All right, well, here's what we're going to have. Actually, let me do this in the equation editor. It'll be a little bit quicker. If we start, so what we're saying here is that if we take the one, well, actually, no, one more step, and then we'll use the equation editor. What we still have to do is this. We have to divide both sides by 100 before we take any exponents. All right, so now 1240 over 100 equals B raised to the 10th power. Okay, hold on. Yeah, the exponents are really awkward in PowerPoint. That's why I think it might be better to use the equation editor. 1.24 is equal to B to the 10th. Yeah. So what I need to do now is raise both sides to the 1/10th power. In other words, I need to offset that exponent. And the way to do that is with its inverse. Okay, so in other words, in my equation editor, what I'm going to do in order to get rid of this exponent of 10 is raise both sides to the 1/10th power. All right, see how much quicker that is? Okay, 1.24 to the 1/10th power equals B. Okay. Wow, for some reason it's really tiny here. Oh, much better. All right, so this is what we needed to do. It doesn't seem to want to move. I'm not sure what's going on here. Oh, here we go. No. Yeah, PowerPoint doesn't always work the way I'd like it to. The hell is this? No, all right, I'll just leave it there for now if it wants to be that stubborn. But anyway, the bottom line is that B equals, if you take out your calculator and take 1.24 and raise it to the 1/10 power, you'll get 1.021744, which means now the B is 1.0244. The actual growth rate is B minus 1, which is 0.021744, which is 2.1744%. Oh, wait a minute. No, I just realized I completely screwed it up. You know why? I knew something wasn't right. 1240 over 100 is actually 12.4. No wonder it doesn't look right. No, the stock grew a lot faster than that. All right, you know what? Let me start this again. Let's get rid of all this crap. I'll just do it. I'll put up with the very poor facilities of PowerPoint. Yeah. All right, so that's where I made the mistake. So 12.4, now the exponent here will be 1/10 power. And so this has to be an exponent. That's better. All right. So now take out your calculator, 12.4 raised to the 1/10 power, which, by the way, you can make this a lot simpler on yourself just by converting that to 0.1. Okay, so now if you change the exponent from 1/10 to 0.1, it'll be a lot quicker and easier to figure this out on your calculator. All right, so finally, after all that, yeah, this is a lot more like it. It's 1.2863 equals B. So the actual growth rate of the stock is B minus 1 rather, which is 0.2863, 28.63% per year. So that's how fast the stock price grew over those 10 years. I probably should have written it out by hand. It was such a hassle. But anyway, so the bottom line here is that this is a classic case of what you can do with your exponential functions. You can easily use it to figure out the growth rate for any investment that you may have made. So again, the stock went from 100 to 1240 over 10 years. So P of T will be used to represent the price at time T. P of 0 is the initial value of 100, and that's our A. P of 10 is 1240. So using this expression, the A becomes 100. P of 10 is 1240. We end up with 1240 equals 100, B to the 10th. Now we want to divide out that 100 from both sides. Isolate the B. We've got 12.4 is B to the 10th. We get rid of that 10 by raising both sides to the 1/10 power. And so 12.4 to the 0.1 power is approximately 1.2863. And that implies an annual growth rate not of 128.63, but minus 1, which brings us down to 28.63% per year. All right, so now in the next example, we have a silver dollar that was minted in 1899 that is now worth $37.42. Now let's pretend that it's 2019, by the way. Okay, so in other words, the coin was worth $1 in 1899. It is in 2019. 120 years later, worth 3,742 to collectors. Now, by the way, any coin or note ever issued by the US government is still legal tender. You could take this coin into a store and spend it for $1, but you'd have to be crazy because it's worth a lot more than that to collectors. The silver content alone is probably worth at least 40 or 50 bucks. So the fact that we can sell it to another investor for 37.42 means that we've had a growth rate. So here, okay, here I use V for value instead of price. It doesn't really matter. So this is the final value. This is what it's worth in 2019. This is what it was worth in 1899. You notice this time the exponent is 120. I divide both sides by 1. Well, that's not really necessary. So 3742 equals B raised to the 120th power. And now I take the 1 over 120 power of both sides to eliminate this exponent. And that works out to about 1.0710, or approximately 7.10% per year. So that's a lot of growth. But this way we know. Now, the nice thing about having this information is that we can now compare two different stocks or any two investments we choose side by side and compare how well they did for us by looking at that annual rate of return, because that's really the bottom line, the annual rate of return. This is how I judge the success of my investments. All right. Now, what if I need to find an exponential equation from 2 points? Now, we've done this before with linear equations, and it was a very simple process. So there's no reason why we can't do the same thing with an exponential equation. So let's say, for example, we have 2 points, -2, 6, and 2, 1, and we know that there are 2 different points on an exponential function. How do we know what that function is? How do we figure this out? All right. Now, this is a little messier than what we've been used to doing with linear equations, as you can probably guess, but it's not that bad. It's just that we tend to end up with a lot of very messy numbers. So here's what we're going to do. First, I pick one of the points and plug it into this function. Okay, so the 6, remember, this is x -2. 6 is, of course, x comma y, but y itself is f of x. So this point can be thought of as x comma f of x. So therefore, this gets substituted in for f of x, and this gets plugged into the x. So I have 6 equals ab to the -2 power. Now, how does that help me? I've still got 2 variables in there, and I don't know what they are. So what can I do? Well, how about if I do the same thing with the second point, 2, 1? Aha. So remember, f of x is ab to the x, and this means that's my f of x, this is my x. 1 equals ab squared. So I now know 2 things. So what can I do now? I can solve for both a and b with the method of substitution. Now, this can be carried out in several different ways. Basically, what I need to do is take one of these equations and rewrite it in such a way that it is an expression in terms of either a or b. Like, for example, I could easily take this one and rearrange it to be a equals 1 over b squared, or a equals b to the -2 power. Once I have that information, I can plug that back up here and solve for b, okay? Because this tells me that 6 equals b to the minus 2, b to the minus 2, or 6 equals b to the minus 4 power. Oh, wow, that's a bit of a mess, but we can do it. How? Well, what you can do, in fact, this is the way I chose to go. Let's jump down to those slides. 6 equals b to the minus 4. If you want to, you can rewrite that as 6 equals 1 over b to the 4th. And then, which I've done here, you can multiply both sides by b to the 4th. And so that means that 6b to the 4th equals 1, or b to the 4th is 1/6. Now all you have to do is raise both sides to the 1/4 power, and you'll get your result. So therefore b equals 1/6 to the 1/4 power. Okay. And if you plug that into your equation, your calculator rather, this 1/6 to the 1/4 is approximately equal to 0.6389. Now, what about A? Well, remember, one of the two equations was that 1 equals AB squared. Okay. So we can then claim that 1 over B squared is A. And if you plug that into your calculator, you're going to wind up with approximately 2.44. Hold on. Let's say 2.4498 equals A. Give or take a little rounding. Okay. So that's what I did here. I took the second equation, I plugged in B, and I ended up, we're almost done here. You can see A equals approximately 1 over 0.4082, which is approximately 2.449. So I've now got A at 2.449, and B is 0.6389. So therefore, f of x, remember, is a b to the x, can be now written with the exact constants, 2.449. And here, just to keep it a little clearer, or cleaner, I guess, 0.6389 raised to the x power. That is your exponential function. Wow, that was a bit more complicated than what we had to do with the linear functions. I'm sure you'll agree, but it works. Okay, it's really just a question of identifying two equations in terms of A and B and solving them with the method of substitution. Now, the algebra might be messy, but the process is pretty straightforward, just not as straightforward as for linear functions. Okay. All right, and this is what it actually looks like. When all is said and done, this is what our function looks like. All right, so now we're going to look at another example. This one involves money, but in an indirect way. We're going to be looking at interest. Okay, now, of course, everybody, even if you've never had a bank account in your life, everybody has heard of the word interest. Interest is what you pay when you borrow money, but it's also what you earn when you save your money. Okay, so if you bring your money to the bank and set up a savings account, they'll give you an interest, some amount of interest that gets tacked onto your balance every so often, so that you're actually earning some kind of rate of return on your savings. It's not a very large amount at this point in time, but still, it's better than keeping your money in your pockets or in the drawer or whatever the case may be. So, but calculating the amount of interest that you've earned on a savings account or on an investment of some kind can be fairly complicated. So we're going to be looking at how interest rates can be calculated using these exponential functions. This is a classic example of when you might actually need to use exponential functions. All right, so let's take a look at this. When we borrow or lend money, the borrower pays interest to the lender. That's the bottom line. So if you go to the bank to borrow money to buy a car, they'll give you the money, all right, but of course you'll pay back the original principal plus interest. So you'll end up paying more than what you borrowed for the car. So for example, just as a quick example, suppose that you borrow $20,000 to buy a car, and the bank offers you a loan that will take 5 years to repay. So let's imagine that, suppose that the monthly payments are, now I have to do a quick calculation here to figure out something that makes sense. Let's see. Okay, so let's say that the monthly payments are $450. Okay, so after the 5 years are up, or after the loan has been repaid, the total value of these payments will be, so that means you've made 60 payments of $450 each. 60 because it's 5 years of monthly payments. So 60 times $450 is $27,000. Okay, the additional $7,000 that you repaid is the interest on the loan. So in other words, because you borrowed the money and didn't pay for it yourself, you had to borrow, and of course the bank will charge you interest, and because of that you'll end up paying more than you originally borrowed. The difference between what you borrowed and what you pay is the interest. Now, what we would like to be able to do is figure out, given whatever interest rate the bank is charging, determine how much you'll end up paying for this loan. So in order to calculate properly the amount of interest that you're paying, it turns out that there's really two basic kinds of interest that you're paying. You have interest on the original borrowed principal. In other words, when you bought a car for $20,000 and you borrowed $20,000, that $20,000 is called principal. The rest, so the interest that you pay directly in that principal is one type of interest, which we call simple interest. And then we also pay interest on the accumulated interest. That type of interest is known as compound interest. So of the $7,000 that we paid before on that car loan, some of it was simple interest and the rest was compound interest. How do we know how much of each we're paying? Okay, well, that's a very good question. So we're going to use a special formula, which you'll see resembles very closely the exponential formula function when we calculate how much we repay for a loan. So let's take a look at this thing. So basically, you can imagine, and remember, the functions we had earlier look like this. So you can think of this as your A, and all of this is your B, and this is your X. It is, in fact, an exponential function. But what do these letters actually mean? By the way, oh, sorry, this is your f of x. All right, so it's written this way for a specific reason, because this is a special case where we're looking at or trying to determine how much money we will either pay or earn when we borrow money. So this A term is called the future value. The P term is called the present value, or no, sorry, this is the principal, but it's sometimes called the present value. Let me put a note here. We're going to call it principal, but it's also known as present value. R is the rate of interest. Now, T is time, but there's one complication here that we didn't get earlier with our original function. And that is this. N represents the number of times per year that interest is what we call compounded. Okay, so let me, in a second, when you're through writing all this down, I'll show you what that means, compounded. All right, are we done copying? Okay, so what do we mean by compounded? So for example, suppose a bank charges, or let's say a bank pays 4% on its deposits to savers. If the interest is paid at the end of the year or once per year, then the interest is said to be compounded annually. And it just simply tells us how often the interest is credited to our account. This applies to both borrowing and lending, by the way. But suppose that instead of it working like that, suppose the same bank, oh, let me go back to this for a second. So this is annual compounding. In other words, once a year, we get paid 4%. Okay, now, what about this situation? What if instead the bank says, you know what, going forward, we're going to change the way we do things here. We're going to, instead of paying 4% once a year, the bank decides to pay 2% twice per year. Okay, this is known as semi-annual compounding. Okay, so in other words, instead of getting 4% at the end of the year, every 6 months you get 2%. We call that semi-annual compounding. Semi means half. Twice a year, or every 6 months, or every half a year, you get paid interest. If you're the borrower, a lender rather, if you're the borrower, you pay that twice a year. Now, what about this case? Is it possible then that instead of paying twice a year, maybe the bank will pay 4 times a year? So how about this scenario? Instead, the bank decides to pay 1% 4 times per year. This is known as quarterly compounding. So in other words, the bank can choose any frequency of compounding that it wants to, and that will determine how often you get paid interest. Is it once a year? Is it twice a year? Is it 4 times a year? And it can potentially go all the way up to every single day. All right. So that's the range of possibilities. You can have anything from once a year to once a day. Now, the way this works is that if for a borrower, the more frequently interest is compounded, the more interest he or she will pay. On the other hand, for a lender or saver, the more frequently interest is compounded, the more interest he or she will earn. So if you're saving your money, you want a high frequency of compounding. If you're borrowing, you do not want that. Okay, so, but that number will tell us how much interest we're actually earning or paying. It will help tell us. Now, here's a little side note, though. In practice, banks usually compound interest every day. Okay, so in other words, daily is the normal in the United States. So that's helpful to savers, but it's harmful to borrowers, of course. Now, as far as our formula goes, though, remember before we said N represents the compounding frequency, or the number of times a year the interest is compounded. So in other words, if we, like we were saying before, if we compound the interest twice a year, then in our formula, N equals 2, which represents being paid interest twice a year. If the interest is paid every month, that number goes up to 12, which means we're getting interest 12 times a year. And finally, if the interest is paid daily, N is equal to 365 because, of course, there's 365 days in the year. So what we're going to do is now calculate the interest, of which, remember, we said before, some of which is simple and some of which is compound. Now, for compound interest, actually what we're going to really do here is we're going to do this in an indirect way. We're going to calculate something called simple interest with a very simple formula. If we know the principal that was lent or borrowed, the rate of interest, and the time, the product of those 3 variables will give us our simple interest. The total interest on a deposit or on a loan or whatever the case may be equals the total amount we paid minus the total amount we borrowed or lent. The compound interest is the difference. So let me just bring you back to that last example with the car so we can see what this is all about. Let's go get this car example. Here it is. Just to make this a little clearer, so remember, we borrowed $20,000 to buy a car, and we end up paying back, we paid a total of $7,000. So this, sorry, 27,000. This means that the total interest paid is 27,000 minus 20,000 equals 7,000. Now, suppose that the interest rate in this loan hold on. Let's see. I'm making up a number that makes sense. Hold on one second. Okay, so suppose that the simple interest or the interest rate charged for this loan is 5%. This means that the simple interest is PRT, principal of 20,000 times 5%, which, by the way, when you use percentages, always convert them into decimals. 5% is 0.05 for 5 years. So if you multiply that out, 20,000 times 0.05 times 5 is $5,000. Okay, so this means that we can now easily determine the compound interest by saying the following. The total interest was 7,000. Okay, the simple interest we've just determined is $5,000. Therefore, compound interest equals the difference between these two. It must be the case that of this interest, 2,000 was compound interest. All right, so in other words, the total interest of 7,000, we can break it down into 5,000 worth of simple interest, and the rest, the $2,000, is compound interest. Now, if we only, by the way, here's an interesting side note. If the interest is only paid once a year, we're not going to actually earn any compound interest. So this is a result of the compounding frequency, this part of it. The more often the interest is compounded, the higher will be the compound interest. All right. Okay, so we're ready to do a full-blown example here using our formula. And we'll see, once again, we need to go through all the same steps that we did here. So first things first, let's assume that we're borrowing money and we would like to know how much interest we'll end up paying on this loan. And then we can break it up into simple and compound. So first, we want to know how much interest we're paying, and then we want to subdivide it into simple and compound. All right, so here's the example. Suppose we borrow $10,000 for 3 years. The annual rate of interest is 6%, but it's compounded monthly. And that means that rather than paying 6% once a year, we'll pay 0.5% every month, because 6% divided by 12 is 0.5%. So we have to pay 0.5% every month for 3 years, The question is, how much interest will we pay for this loan? Obviously, we have to repay the $10,000 of principal that we borrowed. How much additional interest do we have to pay on top of that? All right, so based on the example or the formulas we've been using, the P, or principal that's borrowed, is $10,000. The annual rate of interest is 6% rather. T is 3 because this is a 3-year loan. N is 12 because that's how many times a year the interest is compounded. 12 times a year, or monthly compounding. Now we're going to plug all these into our formula. And it's a messy formula, but I'll tell you what, there are strategies for simplifying it that you can use that should make it easier to calculate this on your calculators. So here's the formula. All right, remember we started with this. So remember, P is 10,000, we borrowed 10,000. The interest rate, 6%, is divided by 12 because these are monthly payments. The exponent now will represent months rather than years, so that will be 36. So this 0.06 over 12 is actually 0.005, which we add to the 1. Now, if you take and raise this to the 36th power, what I would recommend you do on your calculator is do this part first, and then multiply the result by 1,000. So if you go to your calculator and take 1.005 and raise it to the 36th power, you'll have 1.1966805525. And when you multiply that out, you'll actually have 11,966.80525, but you can see that has been rounded to 81 cents. So we've used our exponential function to figure out how much we'll end up paying back on this loan in the next 3 years. Now, we can then do the following. That's how much we paid. The original $10,000 is the principal. So that means we can easily figure out the total interest by subtracting the principal from that final amount. So in other words, if we subtract $10,000 from our 11,966.81, this tells us that the amount of interest that we paid is the difference, which is 1,966.81. Now, that's a total interest. What about the simple and the compound interest? So because the simple interest formula is so very down to earth, what we normally do is, rather than try to calculate compound interest directly, we calculate the simple interest and simply subtract it from the total interest. It's so much easier that way. So if you recall, the simple interest formula is PRT. Very easy. So in this case, what do we get? So there we go. The simple interest, the principal we borrowed was 10,000. R, 0.5% for 36 months is $1,800. Therefore, if the total interest was 1966.81 and the simple interest is 1,800, it must be the case that what's left over, that 166.81, is our compound interest. or in other words, interest on interest. All right. So we're going to do some practicing now. Just a few examples, just to make sure we get what we're doing here. We assume that an investor deposits $1,000 into a one-year account that pays an annual rate of 4%. How much will they have at the end of the year if the interest is compounded? And there's 4 cases here: annually, semi-annually, monthly, and daily. So let's just remind ourselves that in the formula that we've been using, this means that n equals 1, n equals 2, n equals 12, and n equals 365. All right, so let's recap that P equals 1,000, R is 4, and T is 1, because this is only a one-year deposit. So in all of these 4 cases, these 3 numbers will be the same. What will be different is the value of n. All right, so why don't we plug in some numbers? So part A, we have our formula. This is the one we'll use in each case. When you plug in all these numbers, all of this simplifies to 1.04. So you're basically just multiplying 1,000 by 1.04, and your final result is $1,040. All right, so here's your challenge. Why don't you try the next one? Whoops. When n equals 2. In other words, in part B, we're changing the compounding frequency to n equals 2. So what I'd like you to do is take this as your starting point, this formula, and use all the same information except that n becomes 2 now, and see how much of a difference it makes between annual and semi-annual compounding. So why don't you take out the old calculator and see what you can do. Oh, before we do that, I just want to mention here that in passing, even though you weren't asked to do this, of that $40, based on our simple interest formula, all of that was simple interest with no compound interest. So let's see how that changes. Sorry, when n equals 2. All right, let's see how you did. If you plugged in those numbers, what's happening here is that you've actually got 1,000 times 1.02 raised to the second power. So this is equal to 1.02 squared. So what you might want to do is multiply that by the 1,000, and you've got $1,040.40. And you'll notice suddenly there's this extra 40 cents here that we didn't have before. What happened? Well, the simple interest never changes due to the compounding frequency. So that implies that that extra 40 cents must be due to compound interest. So we already calculated earlier that simple interest, and again, this will never change throughout the problem. PRT is 1,000 times 0.04 times 1 year equals $40. That will always be the case. So therefore, since the total was $40.40, the remaining 40 cents must have come from compound interest. So again, if you're the borrower, this is not making you happy, but if you're the lender, the saver, this is making you very happy. All right, now let's try the same problem when n equals 12. In other words, when we have monthly compounding. And let's see what happens. Right. Okay, I'm going to spoil the surprise. Here it is. So in other words, here what you actually would have is 1.00, and then you have a string of threes. Let's say you keep 4 of them, raised to the 12th power. Because 4% divided by 12 is approximately 0.003333. Add that to 1, raise it to the 12th. And, by rounding it to dollars and cents, you should get 1040.74. And if you notice, before we had 40 cents, now all of a sudden we have 74 cents. Ooh. It keeps growing, doesn't it? Yes. So now the simple interest, as we saw earlier, here the total interest is $40.74 because we started out with $1,000. Of that, $40 is simple interest. We've already seen that. That part doesn't change. So the result of all this is that now, instead of 40 cents worth of compound interest, it's gone up to 74 cents. Okay. So it's pretty clear, as you can see, that every time we increase the compounding frequency, the compound interest goes up, which I said before, it works to the benefit of the saver or lender and works against the borrower. All right, one more case. Let's try this with daily compounding, which of course means that n equals 365. Okay, let's try that one. And then we'll be done with, I believe, with this topic. Oh, actually, no, we're going to introduce another formula, a much more interesting formula. But all right, so let's do daily. All right, let's see how we did. Oh, so it didn't go up as much, but still. So 4% divided by 365 is a really tiny number. We have to be careful to avoid over rounding it. So let's say that you would put here 1.000 10959 to the 365th power. That's what you're getting here. And so if you round this to dollars and cents, you're actually getting 1040.81. Okay, so that 81, of course, represents your compound interest. All right, now, suppose we kept pushing this compounding frequency even further and further. Now, in practice, it's typically every day. But what if we decided to try compounding interest every hour, and then every minute, and then every second? Eventually, we would reach a case where the interest is being compounded at every instant in time, and we call that continuous compounding. Now, you would think that if we keep doing this, the total amount of interest that we earn would grow very, very quickly, but it doesn't really work that way. Oh, hold on. Whoops, that's not what I wanted to do. All right. So in that case, the future value formula becomes very, very simple. And now you can see that all of a sudden, it looks just like our formula from before, except for one little detail. Okay, remember, an exponential function is written as f of x equals ab to the x power. What we have here, if you think of this as x, the base is this very special number, which you'll see a lot more of if you go on to regular calculus. E is a constant that's worth or equal to approximately 2.71828, et cetera, et cetera, et cetera. So this is now our A, This is now our B, and this NT part here, RT, is our new X. And of course, A is f of X. But this is reserved, this E is reserved for the special case where interest is compounded an infinite number of times. And so this special case is known as continuous compounding because the compounding takes place at every instant in time, basically. This is the extreme limiting case of how far our money can grow when we put it in the bank account. But you can see this is an exponential function, which concludes for the first time the special term E. Now, E will show up again later on in this chapter, but you'll see it all the time in Calc 1 if you do get that to that point. It just shows up everywhere. You might think such an oddball number wouldn't be important, but then, let's face it, pi is 3.141 something something. It's also a very strange number, and yet we see it all the time. Okay, so let's go back to this same situation we had earlier. We started with $1,000. We deposit the money for 1 year. The rate is 4%, but this time, instead of being compounded every day or every week or every month, whatever, it's compounded continuously. And so when you plug in those numbers, you can see that the compound interest is only slightly higher than what it was with daily compounding. But in a lot of financial modeling, we use continuously compounded rates of interest because they have a lot of very convenient mathematical properties, which you don't get with the other examples we were looking at. So it's important to know that this is the limiting case of how fast our money can grow with compound interest, or if we're borrowing as well. This puts an upper limit on how much compound interest we can earn. Oh, by the way, I skipped over this one, but so when we have an infinite number of times of compounding per period, we call that continuous compounding. The other cases we were looking at, daily, weekly, monthly, et cetera, those are collectively known as discretely compounded rates of interest. So discrete and continuous mean the opposite of each other. Now, once again, let's just remind ourselves what's happening here is that what we're calculating is how rapidly our bank account is growing when we put money in the bank. So what's actually happening here is that we're experiencing what's called continuous growth. What about the opposite case? You might remember from high school physics that a radioactive element has a half-life, which represents how quickly the radioactivity decays over time. So a case like that is referred to as continuous decay. All right, so in other words, the formula we had earlier represents continuous growth. By changing the R to negative R, it becomes continuous decay, which implies that the value is shrinking over time. And often this is used to represent half-lives of radioactive isotopes in physics. But you can imagine other scenarios as well, like the value of your car. You know that it depreciates over time, and in principle, you might be able to use this equation to determine how quickly your car's value declines after you buy it. But again, the key detail is they're simply inverses of each other. All right, well, here we go. Suppose that we have, speak of the devil, look, a radioactive element decays at a rate of 5% per day. In other words, 5% is converted from the radioactive element to lead. This is what happens to it over time. It turns into lead. If we start with 100 grams of this element, how much will still be radioactive after 100 days? So we plug in the numbers. P is the starting point. E, of course, we know that's 2.718, etc. The decay rate is 5%. It's a 10-day period. And so by the time the 10 days have elapsed, we're down to 6.0653 grams of radioactive. How much is still radioactive? 6.0653 grams. And you can see it's much smaller than what we started out with because it's losing 5% every single day. So this is what we mean by continuous decay. And it's a classic example of what we could do with an exponential function. Now we're going to work our way back to the opposite case. Exponentials go along with what are called logarithmic functions. Okay, the two are sort of like the opposite sides of the same coin. I guess you could think of it this way. A logarithm, if you recall from high school, is an exponent taken from an exponential function. In other words, if we're told that y equals 10 to the third power, or 1,000, then the log to base 10 of 1,000 equals 3. This means simply that 10 to the third power equals 1,000. Okay, so you remember logs, don't you? You probably do, but you may have forgotten how they work. The log isn't simply an exponent. So the log of this expression is 3. Okay, so therefore the log to base 10 of 1,000 must be 3 because 10 to the third power is 1,000. Now, logs come in handy in many applications. Like, for example, when you hear about the Richter scale, when earthquakes happen, they give you a Richter scale number. That is based on a logarithmic scale, so that the difference between, let's say, 4 and 5 in the Richter scale is actually a magnitude of 10. In other words, an earthquake with Richter scale 5 is 10 times as bad as Richter scale 4 because it's based on log 10. All right, let's look at some other numerical examples in case you've started to forget how these work. The log to base 3 of 9, for example, is 2 because 3 squared is 9. Okay, so you got 3 here. Here's the exponent. And here's the value that you're taking the log of. And similarly, because 2 to the third equals 8, we can say that log base 2 of 8 equals 3. Now, does your calculator have this built into it? If you're using the iPhone, I suspect the answer is yes. All right, so let me go look at it. I'm going to get out my iPhone calculator and see if it's on there. I'm pretty confident it has to be there. Now, remember, your iPhone has actually 2 calculators. If you hold it up and down, it's just your standard run-of-the-mill basic calculator. Couldn't be any simpler. But if you turn it sideways, suddenly it becomes a very powerful scientific calculator. And if you look on it very carefully, oh, here we go. I see, oh, I'm kind of disappointed by what I'm seeing here. I only see 2 logs here. Oh, that's awkward. I see a log base 10, and I see another interesting one, which we're going to get to in a minute anyway. If you look on your calculator, let me add this in here real fast. On the calculator, the iPhone calculator has buttons for log base 10, 10. Okay, now I hate doing exponents on this thing. Yeah, it's being its usual pain in the butt self. It's very awkward the way they set this up in PowerPoint. It's quite annoying, as a matter of fact. It just refuses to switch back. Bitch. All right. LN. Now, LN is a special case. This stands for natural log. And this is the same thing as log. This is the same thing as log to base E. Okay, so E, remember before 2.718, that's what this is for. You might not think that this is so important, but it really is. Anyway, that's what that represents. So they're both on your calculator. So let's do a couple of quick examples to make sure we understand how they work. So for example, let's try log 10. Log 10. Of, let's say, 10,000. All right, so on your calculator, how does that work? What you're supposed to do, and every calculator is different, is type the 10,000 and then type the log button. Hold on one second. So if you type 10,000 and then type the log 10 button, you don't have to do anything else. It'll come back with the correct answer of 4. And why is this happening? Because what it's trying to tell you or remind you is that 4 to the 10th is 10,000. All right. So let's try a couple more just to make sure we understand. And let's do some fractional powers while we're at it. Let's try very quickly log 10 of, let's say, 1,000,000. All right, so you'll type on your calculator 1,000,000 log 10, and it should give you a 6. And that's again because 10 to the 6th is 1,000,000. Now let's try the opposite direction. Let's try a very small number. Let's say, for example, I want to know the log base 10 of 0.001. All right, so go to your calculator and type 0.001. Hit the log 10 button, and you should discover that whatever this number is, it's negative because this is a fraction. And in fact, it's -3. Why? Because 0.001 equals 1.0 times 10 to the -3 power. All right. All right, here's another one. Let's try log base 10 of 0. All right, so another 0, log 10, key. Let's see how it reacts to that. 0, log. Oh, it doesn't like that, does it? Yeah, it won't accept that because there is no value of x such that 10 to the x equals 0. And the same thing will happen for negatives as well, okay? The log of a negative number, of any negative number, will just be undefined. They're both undefined, so therefore you'll get an error message. All right, now let's see why this is happening. Let's go to Symbolab and take a picture or look at what this function actually looks like, just like we did before with e to the x. Why don't we now focus our attention on log of x. Maybe I deleted it. All right, hold on. Let's go find Symbolab again. I just want you to see what this log function looks like. Okay, so log base 10. Oh, here it is. Log, oops, wait a minute. Log base 10 of x. Let's hit go. And let's see what this thing looks like. Oh, there you go. So in other words, you can see the vertical axis is an asymptote. It's never going to be possible for y to equal 0. Okay. I'm sorry, x to equal 0. Y can equal 0, but not x. Right. Y equals 0 right here. But x can never be 0. That's an asymptote to the function. It's always going to be in either the first or the fourth quadrants. And while y can be negative or positive, so the range is all real numbers, the domain is restricted to strictly positive numbers. In other words, not zero. Everything else can go into this function, but not zero or any negative numbers. So if you try to take the log of zero or a negative number, you'll simply get an error message. Wow. So that's why this is happening. All right, so there's a lot more discussion now. Really what we want to focus on next is the algebraic properties of logarithms, because they're actually quite interesting, and they can be used in a lot of situations where we have a very complex equation to work with. They can really help simplify a lot of extremely messy functions that you might encounter in the real world. So that's why this is so important. So I don't want to rush through this part. In fact, I think maybe we can stop right about here and pick it up with our discussion about logs, not just how do we calculate them on the calculator, but all the important properties that they have and the algebraic operations we can perform on them. And so we can save that for next time. And then when that's done, we'll pick up with chapter 5 as well, which is our introduction or review, as the case may be, to trigonometry and trigonometric functions. When was the last time you thought about sines and cosines? Well, if it's been a while, you're going to be meeting up with some old friends again next week after we're done with chapter 4. So in the meantime, between now and next week, what you should be doing is working on the midterm. And if you're done with it, you can come back here and revisit chapter 4 to see and remind yourself what we've been doing here, and then even read ahead a little to see all the interesting properties of logarithms that we're going to need, because they will show up everywhere in math, not just here. Everywhere you look, you might potentially run into logarithms, okay? Especially because their properties are just so useful. So in the meantime, I guess if there's no last minute questions, I think we'll stop right about here, and then we'll carry on next week. No, just keep working on the midterm, and I don't think we will have anything. No new homeworks. Just work on the midterm, and then flip to the slides and refresh your memory about what we've been doing today. Yeah, just take pictures of it or scan it and just email it back. Try to send it to my purchase account. It'll just be easier for me to keep them organized. All right. Anything else?
Thank you for your time, Professor.
All right. I'll see you
Thanks,
next
Professor.
time. All right. Bye. All right.